starting with our skeletal system. I'll turn one of the lights off too. Oh, I'm afraid if I plug this in, it's not going to either record. Hold on. Or it's not going to do something. Is it still recording? I still have sound. I hope I still have control. Just fast forward 30 seconds if you watch it at home. Again, as we go through it, I'll shrink that too. Common prefixes when it comes to the bone. Yes, you're going to see osteo in a lot of stuff. And today you're also going to see chondr in a lot of stuff too. Because as we talk about bone, we always talk about cartilage as well. Because bone comes from cartilage. Everything starts with cartilage. And I'm like, when infants and fetuses are developing, they don't right away have bone. Everything starts off as cartilage. So you're going to see chondr in a lot of stuff. You're going to see osteo in a lot of stuff. So, as we start talking about cartilage, there is cartilage found in the skeletal system. It is water-based. It has lots of water on it. Now, my cartilage tissue itself has lots of water in it. Part of that is that it's bendable. It's got some give to it. And we need that around and found near our bones. Now, it also has no blood vessels or nerves in the actual cartilage tissue. And I'm like, so it in itself does not heal very quickly. It doesn't have its own blood vessels to supply it nutrients. So it takes a really long time when you damage cartilage. Now, as we talk about cartilage, yes, you're going to see chondr in a lot of stuff. Chondrocytes just means a cell, a cartilage cell. It's found in space. In lab this week, in your compact bone, there were lacuna spaces that contained osteocytes. Well, in your skeletal cartilage, there are also lacuna, which are space, that contain chondrocytes. So the lacuna are always the space that contains some type of cell. If it's bone, it contains osteocytes. If it's cartilage, it contains chondrocytes. It will also contain some of the extracellular matrix, the fluid that makes up the tissue. There are 3 types of cartilage we find in our skeletal system. We find hyaline cartilage, which is the most common. We find elastic cartilage, and we find fibrocartilage. Hyaline cartilage, which we find the most of, and I've got a nice little picture on the next slide that shows you all the places you can find hyaline cartilage, provides lots of support, provides lots of flexibility between bones, lots of resilience, which means as you have bones hitting bones, there's some resilience there. Now, it only has collagen fibers, and lots of the places we find it, articular cartilages, which means anywhere you have bone meeting bone and have movement. Anytime you articulate, it's where movement happens. So anytime you have bone meeting bones on the ends of every single one of the bones in your fingers, you have articular cartilage, because that's where you have bone meeting bone and you have movement happening. You have it in your costal or your rib cartilage. You have it in your respiratory areas that line the respiratory tract. And you have it as your nasal cartilage. When you squish your nose, that's hyaline cartilage. Elastic cartilage, similar, but it contains those elastic fibers. It's a little more stretchy. It's a little more rubber band-like. And that's your external ear. You can stretch your ear and it bounces back. And I'm like, you can fold your ear forward and it flops right back. It's because of those elastic fibers. And then there's the fibrocartilage, which is a tougher cartilage. And it's found between bones where there is lots of force. And the top places we find that, the menisci of the knee. When you think about the force every time you take a step, there's lots of force there. It's also between all of your vertebral discs because of all the force you're putting on your body just walking around. And it's also found in between your hip bones, where your hip bones meet. Now, my picture is, because your hyaline cartilage, the most common one, is all the blue. Found between every bone area where you have lots and lots of movement, articulation. And I'm like, your fibrocartilage, that really tough cartilage, found in the knees, found between the vertebrae, found between your hip bones. And your elastic cartilage we find in your ears and also in your floppy little epiglottis. Now, our cartilage grows just like bone grows. Our cartilage grows wide, and it can grow long as bones grow long as well. Appositional growth always means growth with. The This is the same for bone as well. Anytime your cartilage grows out, it's wider. It's called appositional growth. Anytime the bone or cartilage grows longer, it's called interstitial growth. All bone is starting off as cartilage. Now, we can calcify our cartilage, but that's not the same thing as your compact bone. So we can add calcium to cartilage to make it hard and bone-like, but it's not going to give you those little tree ring-looking structures that's going to be found in your compact bone. And so we can harden and calcify cartilage to make it bone-like, but we don't technically call the calcified cartilage bone. It is still really hard, and we still find it in and amongst bone tissue. Now, as it grows wide, as you use your bones, as you put pressure on your bones, and your bones can grow wider. As you get taller, your bones grow wider. As you put pressure on your bones and use your bones can grow wider. Now, what helps make your bones grow wider, and is we have two main kinds of cells, and I know later on I talk about these cells too, osteoblasts and osteoclasts. Anything that has the blast in it means these are building cells. So if you're an osteoblast, your main job is to build bone. That's what the word means. An osteoclast, clasts do the opposite. They break down bones. If you can think this, the B and B, blasts build, and then clasts do the opposite. They break down bone. So when your bones are getting wider, here's my circular bone, I'm looking long bone, long-wise. We're going to add, the osteoblasts are going to add tissue on the outside of bone to make them wider, but we don't want to just keep making them wider and wider and wider and wider, or what's going to happen to the weight of the bones? If you started off with, tiny, skinny little baby bones, and you just kept adding tissue, and you just kept adding tissue, and kept adding tissue, it's going to be a really heavy bone. And it's going to be exhausting to carry your bones around everywhere. So as we build tissue on the outside, making it bigger and bigger and bigger and thicker and thicker and thicker, your osteoclasts are going on the inside of the bone, the endosteal surface, endo means inside, and they start breaking down some of the bone. So that you still have the same thickness of your bone, it's just a whole lot wider. So the osteoblasts are going to add tissue to the outside of the bone on the periosteum. It's not on there. It's on there. And the osteoclasts are going to remove bone on the inside, on the endosteal. Now, there's usually more building than breaking down. That's why it gets larger, because we want nice, thick, strong bones as you grow. However, we have to break some of them down because we don't want them too heavy. Now, growing longer bones, because you need to grow taller. Your long bones grow longer on the ends of your long bones. So this is why it's nice. I'm glad in lab we already went over parts of the long bone. The epiphyses, the ends of the long bone, there is something known as your epiphyseal plate. That plate found in amongst all of that spongy bone is a cartilage. And that's where new bone is getting formed. And as new bone gets formed in the ends of your bones grow longer and longer and longer as you lay down new tissue. Now, what happens as you get older, that epiphyseal plate starts to get thinner and thinner. We're starting to lay down less new bone. It means you stop growing. And that epiphyseal plate, we will eventually, because that's nice and thick right there, nice cartilage, it's blue, and will eventually become a tiny, skinny little line, almost at the point you can't see it at all. It almost becomes imperceivable that there was ever anything there. So when the epiphyseal plate squishes down to a line, we call it epiphyseal plate closure. It's the end of something. It's the end of your growing. Your long bones are as long as they possibly can be. You're as tall as you possibly can be. Now, the epiphyses, diaphyses, they fuse together. It's one big bone. Females' long bones stop growing at about 18 years old. Male long bones stop growing at about 21 years old. Now, it's about. I'm like, I swear I stopped growing when I was like 12. And I'm like, and it's about. And I'm like, it's approximations. I'm like, there's times I'm like, you hear females that are in gymnastics that put so much pressure on their bones all the time that they can't grow longer. As soon as they stop gymnastics when they hit college, they'll grow like 6 inches. And I'm like, it's about. So females stop growing around 18 and males around 21 years old. Yeah. It's usually hormone-based. Yep. That's about it, is hormones. And I'm like, usually females start growing taller sooner, and then eventually males catch up. It's hormone-based. That's why if you ever walk into a middle school, it's almost a guarantee all the females are taller than the boys in middle school. And then eventually they all get caught up. And then it finally evens up. Now, there's different cells in our bone. There's also different types of tissue. So there's different types of bone matrix, and there's different types of tissue, or different types of cells. We'll get to the cells in a minute. But there's two main characteristics, two main types of tissues. Now, Mike, two main types of compounds found in our bone that give it some of the characteristics that it has. One that it's really hard and strong, and one that it's also flexible, so you can be both. And our bones are both. And I'm like, we have bone cells that make this bone matrix that makes it soft, that make it hard. All the bone cells that lay down new bone become trapped in the bone. So if there's ever cells inside the bone, if they literally made bone, then they became trapped in it. But it helps make the bone strong. And as bone cells, as they lay down new tissue, become trapped in it to make our bones nice and strong, those bone cells will eventually start to break down bone. We are recycling our bone all the time. I'm like, every year, the cells that have laid down new bone will break some bone down, and we make brand new bone. We are constantly recycling bone. I think it's like every year, 5 to 7% of your bone is broken down and replaced. We want new, fresh bone. And I'm like, not old, brittle bone. Now, yes, there's extracellular matrix. And I'm like, different types of tissue, different types of substances in our bone. And then we also have lots of cells in our bone. We'll get to the cells in a little bit. I want to focus on some of the things found in our matrix that gives our bones its characteristic, the strength and the flexibility. Now, of our matrix, we break it down into organic and inorganic. What's organic mean? Carbon-based. And inorganic then? Non-carbon-based. And our two inorganic compounds, non-carbon-based, calcium, that's not carbon, and phosphorus, also not carbon. And I'm like, our organic, we've got collagen, we've got some sugars, we've got some other proteins, all carbon-based things. I'm going to focus mostly on the collagen part of the organic matter. Now, by weight, you have about 35% of your bone is the organic. And I'm like, the proteins, the collagen, the different sugars in there, and about 65% is inorganic, the calcium and the phosphorus. Now, as bone is laid down, these different types of compounds are put in there, and I'm like, they eventually surround all of the cells. The osteoblasts that laid it down become osteocytes, and they just hang out in there. But I want to talk about what the organic part does. So the top part of the organic tissue that's in there is collagen. 90% of the organic matter is collagen. It provides strength to your bone, but the biggest thing collagen provides is flexibility. Our bones can bend. They can. I mean, if I took one of your bones and I'm like, it wouldn't look like it was bending, but it bends a little bit. And we want it to bend a little bit so that if you jump off the table and you jump onto your feet, your bones don't just shatter. Our bones have some bend to it, and it's the collagen that allows it to do it. Now, our cells are also considered organic, but we'll get to them later. And then there's also some proteins and some sugars as well that give it some strength. But the collagen allows our bones to have that bendable flexibility. The inorganic part, the calcium and the phosphorus. Yes, they are bound up in those really big, huge structures. I don't care that you know their names, just as long as you recognize there's calcium and phosphorus in there. I'm like, of all the inorganic compounds, it's almost all calcium and phosphorus with some other compounds found in those big, huge, large names and formulas. And the calcium phosphorus is what makes our bones so strong. Now, if you removed collagen from the bone, what would happen to your bone if you jumped off the table? It would break. Why? It wouldn't have the flexibility. If you removed the inorganic component from your bones and you jumped off the table, what would happen? It would bend. I was going to say it would be kind of bendy, be like flexible. But unfortunately, it'd be so bendable and flexible, you wouldn't be able to stand up anymore. And I'm like, you'd just be a little bendy person. So I'm like, they each serve their purpose. Really strong bones, but also flexible bones. I'm like, we need both. Now, this is showing what can happen if we remove either of them. If we remove the calcium, if we remove the calcium and the phosphorus, if we remove the stuff that makes your bone strong, you can bend bone. This is why I'm like, again, I was bummed we had to replace it. I'm hoping Deke's going to do it. And I'm like, that if you soak bones in vinegar, it removes the calcium and the phosphorus off, and your bones become super bendy, and you can just bend them. If you remove the collagen, the part that makes your bones flexible, and you jump off a table, that's what's going to happen to your bones. So I'm like, they would shatter into 1,000 pieces. I'm like, we need both of them for bone health. Now, one condition that can happen if we're not getting the correct amount of our inorganic component, it's a condition known as rickets. Now, rickets means osteomalacia, and I don't know if I had that on my first slide or not, but malacia means soften or softening. And so osteomalacia means soft bones. Now, what happens with rickets, because I think I talk about later in this semester, or later in this PowerPoint too, but that's on the video you have to watch at home, is that the most commonplace or reason why rickets happens is that there's not enough vitamin D production. Because we'll talk about how vitamin D is important, but we need vitamin D to absorb calcium. This is why if you go home and you look at your milk container, guess what's inside of your milk? What do we add to milk? Vitamin D. It's vitamin D fortified, because without vitamin D, you can't absorb the calcium that's in the milk. You can't. And I'm like, we need vitamin D to absorb the calcium. So what can happen, and I'm like, if kids are deficient of vitamin D, they can't absorb the calcium. And if you can't absorb calcium, what happens to your bones? They bend. And that becomes very evident when kids start walking. And I'm like, that their bones become bendy. So I'm like, we need vitamin D. Now, good place we can get vitamin D, any guess? Other than your milk? The sun. The sun, your skin can make vitamin D. UV radiation on your skin can cause you to make vitamin D. So it's like, yay. I'm like, not too much UV, or get skin burns and skin cancer, but your skin, and I'm like, can actually make vitamin D. Now, calcium, we need it. I'm like, yes, dairy products as well as other fruits and vegetables, most of the vegetables can give us calciums as well. We need calcium, not just for our bones. We need calcium ions, and we'll get into it when we get into muscle cells and heart contractions. We need calcium in lots and lots of places. We need it in our membranes. We need it in our neurons for them to fire correctly, because we'll get that in our next unit with neurons. I'm like, we need lots of calcium, not just in our bone. I'm like, but guess where most of the calcium in your body is stored? In your bone. So what happens if you're not drinking enough calcium? And our body needs calcium. Where's it going to get it from? Our bone. And I'm like, our bone is a storehouse of calcium. We want it there to make bone strong, but if you're not getting enough calcium in your diet, our body will go to your bones and start breaking your bone down to get that calcium out of there, because we need calcium in other parts of your body to survive. And so we have calcium regulation. There are two main hormones. You have to know these. I know these hormones are on your next quiz. And I'm like, are on your test on Tuesday. And I'm like, you have to know the hormones. And I'm like, there's one called, and I don't even know if it's on my sheet up there, or on my slide. One's called the parathyroid hormone, and one's called calcitonin. The parathyroid hormone. I don't know if I have to write this down. I can write it. Its job is to break bone down. And why would we need to break bone down? Well, we will, but we need something before that. What am I talking about on this slide? Calcium. So I'm like, if you're not getting enough calcium in your diet, that you need calcium, because your blood calcium levels are too low, you're not getting calcium in your diet, the parathyroid hormone will break your bone down to release calcium. Now, the opposite, because I've got another picture on the next slide, is another hormone called calcitronin. It even has like calcium kind of in the word. It does the opposite, and it tells our body to absorb calcium, I think it's +2, into bones. So that means you just got done, drinking a glass of milk while you're eating a bowl of ice cream, and I'm like, while munching on some cheese curds, you got as much calcium as you possibly can have in your body. That's lots of calcium in your blood. Well, let's put that somewhere where we can store it. Calcitonin allows our body to take the calcium from our blood, store it into bone. Now, for us to make this hormone, guess what vitamin you need? Vitamin D is needed to make calcitonin. Calcitronin. Is it? I don't think there's an R. Sorry. So, before I go to my next slide, and I'm like, calcitonin, parathyroid regulate your calcium levels in your body, in your blood. We need calcium and phosphate to do lots of things. We do lose some of them in our blood. We do lose some of them in your urine. So they have to be replaced all the time, which is why you have to be constantly getting calcium in your diet. If you don't get it from your diet, the parathyroid hormone is going to remove those calcium ions from your bone, making your bones weaker. Now, exercise and nutrition will help keep your bones strong as well. It kind of triggers that calcitonin to work. But here's kind of that balance. If you're, we're on an imbalance. If your blood calcium levels are too low, so your stimulus is following blood calcium levels, the parathyroid gland releases the parathyroid hormones, and it triggers bone-breaking cells, osteoclasts, class break, to break down bone, to release the calcium that's stored there so that we can get calcium ions back into our blood supply and out to whatever part of the body needs it. The opposite, because I don't think I have an opposite. If your stimulus was rising blood calcium levels, because you just had a bunch of calcium in your diet, the calcitonin hormone will tell our body to take that calcium in your blood and store it in the bone. Now, so we always have lots of calcium in our bones, lots of stored calcium there, but you need a constant supply of calcium in your diet. Otherwise, your bones will start to break down. Now, some other parts of the bones, and I like this, some of this is review from lab, but I go into more details. On the outside of your bone is the periosteum. Peri means around, oste means bone, just means it goes around the bone. It's a double-layered membrane, not tall enough to point up there. And I'm like, on the picture, it's being pulled back. There is a fibrous layer, and I'm like, that's being pulled back when that periosteum is there. Now, it's cells. There are cells found in that periosteum that are called osteogenic cells. Anything that has gen in it, it's like generating or making. These are bone-making cells. I erased it. And I'm like, because when our bones are growing, they're constantly getting laid down on the outside, like getting wider and wider and wider. And so we have bone-building cells there, and so we do have lots of osteogenic cells. They're stem cells. They can become other cells other than osteoblasts. I'm like, but we store a lot of our bone stem cells on that outer membrane there. There's lots of nerve fibers. There's lots of blood vessels. So if you ever break your bone, you're going to bleed in lots of different places. And I'm like, and there's also lots of bumps on the outside of the bone because that's where you have lots of tendons and ligaments that are constantly attaching to bone to pull them so that we can move our body. The inside lining of your bone is the endosteum. Endo means inside. And so it lines the inside lining of the compact bone. So it lines that medullary cavity in there. It lines all of the spongy bone that's inside the bone. It lines all the canals that have blood vessels that go all through the bone. And we also find osteogenic cells is there. So we also find stem cells in that inside lining as well. Big zoomed in picture. As I say, I like this. You can see the periosteum getting pulled back. Very fibrous tissue. Endosteum just lines everything on the inside. Now, the cells that we find in there. There are 5 major cell types in your bone, and they have the same basic cell type, but they all have their own little slight variation. There are osteogenic cells. What do? Based on their name. Yeah, they can make bone, and they're ones that they can kind of become other kind of bone cells. There are kind of stem cell ones. Osteoblasts, what do? They build bone. Osteocytes maintain it. Osteoclasts, I'll get to the other one in a second. Break it down, and then there's ones that are called bone lining cells. So I've got a little more information, and some I've already mentioned before. But osteogenic cells, they get another name. I mean, the same thing, it's just longer. Osteoprogenitor cells. It really means, before we're making bone. I like to break that down, Mike. So it's like before we're making bone, these are cells that can become other types of bone cells. Like we're not making it yet, but we're going to become another type of bone cell. These are stem cells that can become other bone cells. They're mitotically active, which means they're undergoing mitosis, so they can make more of themselves, so we can make more osteoblasts when we need it. We can make more osteoclasts when we need it. We can make other types of bone cells whenever we need it. Whenever they get their whatever stimulus of whatever our body needs, they generally are going to differentiate into an osteoblast or some kind of bone lining cells, and I'll get to the bone lining cells. Some will always just hang out as a stem cell, so that we have to have something that can divide. We have to have something that stays there as our stem cells. Now, the bone our osteoblasts, their job is to build bone. They are the bone-forming cells. These are the ones that are laying down the tissue. They're laying down the matrix. They are laying down the tissue. That includes laying down collagen. That includes laying down calcium-binding proteins. These are the ones that are building new bone tissue. They're also actively mitotic, meaning osteoblasts can divide and become more osteoblast cells. Now, looking at them, stem cells, they just look a little more flattened. When they get triggered, they can become an osteoblast, which just looks like a big old cube. It lays down bone. Osteocytes are considered mature bone cells. Their job is just to maintain bone. They are not building bone. They are not breaking down bone. Their job is to maintain bone tissue. They just have to make sure everyone's got everything they possibly need. Okay, we're all good. They're just there to maintain bone tissue. Now, they can communicate to other cells if they need to. And that's what maintaining is good for doing is, they can act as stress or strain sensors to tell bone, okay, well, we've got a lot of stress. Maybe we need to build some new bone and break down the old stuff. And so they can communicate to cells and say, okay, we need to, stimulate our osteoblasts to build new bone because it's getting a little old, and osteoclasts to break bone cells down, so that we have new, fresh bones. If you're a person that you've never worked out ever in your entire life, and all of a sudden you start lifting weights and you are putting lots of weight on your bones, you're triggering your bones. Like, oh, I don't know if we're ready for that yet. Like, our bones are not that strong to handle whatever kind of new exercise you're doing. And that's a trigger that will trigger your bones to start that recycling happening faster. It's like, hey, this person's using our bones more, and we have to make sure we're ready for it so it doesn't break. Let's lay down new bone, and and then break down the old stuff, so we have fresh new bone. Bone lining cells, they are flattened cells. I've got a picture. They're little flattened cells found on bone surfaces. That's why they're called bone lining cells. On the outside of the bone, they're called periosteal cells. Again, peri means around, found out in more of the periosteum area. And they're also found on the internal surface called endosteal cells. They're cells that are usually also maintaining but they can also trigger cells. And I'm like, osteoblasts and osteoclasts. And I'm like, but their job is kind of just hang out. They act like osteocytes, but they're only found on the linings. They're not found in the bone tissue itself. They're just found hanging out on the outside of the bone or on the inside of the bone, helping to maintain everything like the osteocytes do. And then the last cell are the ones that break down old bone. I'm like, are the osteoclasts. They're derived from our hematopoietic stem cells. So these are actually derived from some of our blood stem cells. And their job is to become a macrophage. What does phage mean? To eat, like a phagocyte eats stuff. Macrophage means big eater. I'm like, so these are big eating cells. Their job is to break bone down. Well, they do that because they break it down. They eat it. They are giant multinucleated cells that break bone down. So when you don't get enough calcium in your diet and you have to break bone down, this is the cell that gets recruited to do that. The osteoclasts are there to break that bone down to release the calcium out. They do have kind of a cool ruffled border on one side. And I'm like, lots of surface area so they can secrete enzymes to help break the bone down. So osteocytes, they're just there to maintain your bone. But here's that multinucleated osteoclast, and it has that ruffled border on the one side for lots of surface area, secrete those enzymes, break bone apart. Here's an actual picture of one of these multinucleated osteoclasts, and this part up here, I know it looks like it's separated, it's not, and I'm like, up here is that little ruffled border. So it's breaking down bone. Now, 7 functions of our bone. 1, support. We need support for our body. We need support for our soft organs. We have to have a basic structure. It's all for support. Lots of things anchor to our skeletal system. It's there for protection. We have some of the strongest bones that protect our most vital organs. I'm like, our brain, huge rounded skull. I'm like, that rounded form, just like bridges have an arch, and I'm like, our bone, our skull is rounded. It's a nice, strong shape. We also have our ribs that protect the lungs and the heart. I'm like, we're protecting all of our internal organs. We use it for movement. They are levers. Our muscles have to attach to something, and then we use those bones to move all around. We use it for mineral and growth factor storage. We can store calcium there. We can store phosphorus there. We can store lots of stuff there. We can use it for making blood because our red blood cells are made in our spongy bone. So blood cell formation. Poiesis means making, heme means blood, making of blood. We can use it for fat storage because the yellow marrow part of the bone found in the medullary cavity, that's all adipose tissue. And for some other hormones. There's another hormone called osteocalcin that regulates our bone formation. It protects, other than that, it regulates bone formation. It can protect against obesity, it can protect against glucose intolerance, and it can even decrease the chance of different forms of diabetes. So it's a hormone that's been linked to other things other than just maintaining and regulating bone function. Now, and I'm like, lab-wise, we get into like what happens when stuff breaks, but lab-wise, you have 206 bones in the skeleton. How many do you guys have to know? Although not really, you guys don't have to know the bones of the wrist. So just about all of them, and all the bumps and projections and everything that else is found in there. Now, I know some of you guys are going into the radiography program. Bones, you gotta know the bones. I don't know who's going into the I don't remember. And I'm like, but I think there were 3 or 4 of you guys going into that program. You gotta know the bones. You gotta know every bump on the bone, everyone. And they're divided into 2 groups. The axial skeleton, bones going right down the middle of the body. Appendicular skeleton, which we tackle next week in lab. And I'm like, bones of the arms and the legs and the bones that help attach the arms and legs to the axial skeleton. Different parts of the long bone. Some of this we went over in lab, but I still have to talk about it in lecture. The diaphysis is the middle portion of the long bone. The long, dia means through. You know, if you think diarrhea means through. Diaphysis goes through the long portion of the long bone. Inside of it, you have a cavity. It's never empty. And I'm like, but it's the medullary cavity. It usually has some adipose or yellow marrow in it. The epiphyses are the larger end portions of the long bone, where you're going to find your spongy bone. They're lined or covered with articular cartilage. That's the blue. That's your hyaline cartilage that covers all your articular surfaces. And it's also where you're going to find your epiphyseal plate, if you're still growing longer or taller, or epiphyseal line. I don't like how this is called a line on here, because to me, that's thick enough I can see it. I would say that's a plate still. But you're going to find the epiphyseal plate if it's still thick and you're still growing taller, epiphyseal line if growth has ended. Now, my little notes, it's kind of my fun factoid. I'm like, when they dig up bones out of a grave and they're like, ah, yes, this is the bone of a child and we think it's the age of whatever. Well, if someone died 200 years ago, how do you know it's a child and it's not just a really short person? Because I'm like, I don't know. They could dig up my bones in 200 years from now and they'd be like, oh, it's like a 12-year-old girl. And I'm like, how do you know it's an adult versus how do you know it's a kid? Well, they slice open the long bones. They just need to slice open one, and they look to see, are they growing or are they not growing? As you start to get older, as you start to get to those adolescent years, that plate does start to thin. And I'm like, so a lot of times they judge based on how old someone is from skeletal remains. And I'm like, is the presence of the epiphyseal plate or an epiphyseal line? Other parts is in our compact bone. Also, it's got another name, compact bone, called lamellar bone because of those circular structures that look like tree rings. We also call it the osteon bone or the haversian system. It's just what compact bone looks like. That you've got these little cylinders. They look like tree rings that run the whole length of your compact bone. I've got more pictures. They look like your tree rings, but I'm going to draw more on there. Now, in amongst all of that, I'm like, we do have some spaces, and I'm like, in there, but, and I'm like, the rings themselves is called lamella, and we've got a couple different kinds. But the fact that we've got collagen fibers in those rings allow our bone to bend. I got time. And so because of the rings, and I've got a picture on the rings that shows how it can resist twisting and resist breaking, it's those rings that really does give our bone such awesome strength and flexibility. Now, these are the rings. So you've got the rings that are found inside the compact bone. Each ring is called a lamella. And if you notice, do all the fibers run in the exact same way? In the same direction? They don't. And I'm like, some of the fibers in the lamella run this direction, some run in another direction. Because of all those lamella and because the fibers run in different directions from each other, if bone starts to become twisted, because some of the fibers go in that direction, it actually allows the bone to be twisted without breaking. If all of the fibers ran in one direction and the bone got twisted in the other direction, what's going to happen to it? It's going to snap and break. And I'm like, but because they go in different directions, they allow more flexibility for the bone to get twisted. Now, other parts in there, we've got, in the middle of each of the osteon, you have a central canal, so right smack dab in the middle, you have lots of blood vessels. You also, connecting one central canal to another central canal to another one, we have these perforating or Volkmann's canals. We have small little gaps in there where we find osteocytes, the little cavities called the cuni, that we find osteocytes. And what's the job of an osteocyte? Maintain bone. And we have little tiny, that's not a good picture of it, little tiny canals that connect one lamella or one ring to another ring. Now, those little tiny canals, this is a better picture. When bone is laid down, there's your little tiny canals. When bone is laid down, and I'm like, there's usually some type of gap as all of that new tissue is forming, it doesn't always form up to each other. You're also going to have cells that get trapped in there, and some of those cells die and go away, and you end up with little spaces and little gaps. And so you have spaces where the tissue hasn't formed close together. You also have cells that got trapped in there, and a lot of those are osteocytes. Job of an osteocyte is to maintain bone. It's good to have some of them trapped in there. But because you've got these little areas where nothing formed together yet, it allows this osteocyte to still communicate with that osteocyte. So it allows our osteocytes to communicate with each other as they're trying to maintain our bone. They also permit nutrients and anything else to get from one part of our bone to another. Now, we have two kinds of lamella. Generally, when we talk about lamella, especially lab-wise, we're talking about the rings. However, if I tried to draw rings stacked up next to each other, is it solid all the way through? Is there a gap? There's a gap right there. When you have circular things drawn next to each other, they don't form and stack up very well. And so that space in between the rings is called interstitial lamella. Inter means between. So it's the interstitial lamella. The circumferential, what do you think of a circumference? They go around. But the interstitial is in between. So they're incomplete lamella. They don't get the cool ring structure to it. They just fill the gaps between them. I put on the circumferential, yes, they resist the twisting. More pictures of it, but I'm running out of time. And I'm like, your spongy bone on the very end, because I know I'm almost done. And I'm like, poorly organized. There doesn't look to be any organization whatsoever. However, there is some organization. A lot of the rods of the spongy bone do run in some of the same direction. And it's usually the direction where there's lots of force, where you're putting lots of weight on bone. Some of the rods of the spongy bone do run in, and I'm like, kind of the lines of force, the lines of stress. There are no osteons. There's no things that look like tree rings. And I'm like, they just look like irregularly arranged structures in there. There's the end. I'm just going to tell you all the answers. So if you printed it, you can circle. Fibrocartilage would be found at the knee. That's your tough, hard cartilage. The following that's not a type of a bone cell is the osteoclast, but I just made it up. A group of concentric rings of bone matrix is your osteon. Adjacent osteocytes communicate with each other using the canaliculi. The principal component of bone that contributes to its hardness, what is it? Calcium. I put the big, huge, long name for it. What would happen to long bone, or what would long bone growth look like in an individual whose cartilage and the disc stopped dividing? Well, at that point, if the cartilage and their epiphyseal disc stopped dividing, the long bones would stop growing in length. They're done. Which of the following bone cell types is responsible for initiating ossification of bone? Osteoblasts. They're the ones that are building the bone. And in a patient whose parathyroid glands have been removed, you would expect this person's blood calcium levels to do what? Any guess? It is decrease. And I'm like, because the parathyroid's job is to break bone down to increase calcium. If you remove the parathyroid gland, can't do that. Calcium's homeostatic importance to the body, why we need calcium, is the big one. It's tons of metabolic activities, muscle contraction, blood coagulation, heart beating, all that stuff. We need lots of it. A disease caused by vitamin D, that's your rickets. I'm like, so your job before I see you next class, finish listening to it. A lot of what happens when a bone breaks, a couple different ways that bone can get laid down. Although it looks long, it's not too long because you can skim through some of the end questions. But it's to watch that because on Tuesday, you guys have a test on the skin and the skeletal system. There's also, we're going to start the nervous system next week, so there's an intro video to watch for that. We are starting action potentials right away on Tuesday. I suggest at least skimming through the intro material before Tuesday. There's also a worksheet due if you haven't done the worksheet yet. So I'll collect a worksheet on Tuesday, and you have a test Tuesday. And a lab quiz.